I want to thank the organizer for giving me the opportunity to be here. And I want to apologize for the technological troubles, but I am very good at having this kind of situation in every presentation I give in every corner of the world. So it's just another check. Today I will present to you some ideas on the relation, the interesting relation that appears to exist between the Hamilton principal function in the context of Hamilton-Jacobi theory, so classical mechanics, and divergence functions in the context of information geometry. So these people are all the people with which these ideas have been shaped, and all of them are physicists. So we were not in contact with the information technology, the science of information before this work. So please be gentle if I say something not too much correct in this case. Okay, a brief summary of what is the idea behind Hamilton-Jacobi theory. We start with a mechanical system and the Lagrangian. And we usually see and identify the dynamical trajectories as the solutions of the Euler-Lagrange equations. Now, these solutions are curves on the tangent bundle of the configuration manifold, but we are actually interested in the projection of these curves on the configuration-like manifold. And these curves are uniquely identified by the initial position and the initial velocity. So this is an initial value formulation of the dynamical problem. But we can do something different, which is to start not directly with the Euler-Lagrange equations, but with an action principle. This is a variational formulation of dynamics. So we have our curve, and the dynamical trajectories are just the critical points of the action. So the dynamical object of interest is the action, which is a function defined on curves. And the interesting fact is that these curves have fixed endpoints. So it is no more an initial value formulation of the dynamics. It is a boundary value formulation of the dynamics. We are not interested in the initial velocity and initial positions, but only on the initial and final position and initial and final time. Now, the Hamilton-Jacobi theory, it's precisely a bridge between these two attitudes toward the mechanical problem. So it is a way to connect this initial value formulation with the boundary value formulations. From the geometrical point of view, this happens because you can give a family of slicing vector fields for the vector fields associated with the Lagrangian. But essentially, the object that does the job is the solution of the Hamilton-Jacobi equation, which is the Hamilton principal function that I denoted with S. Incidentally, this coincides with the action functional evaluated on a dynamical trajectory, but this dynamical trajectory must be found using the Euler-Lagrange equations. So this function is a generating function for a canonical transformation describing the dynamics, and it is the bridge between the initial value formulation, so the dynamical trajectory defined by the Euler-Lagrange equations, and the initial value and the boundary value formulation defined by the action functional. So we want to connect these objects, the Hamilton principal function, with divergence function in information geometry. So in information geometry, what we have from a purely mathematical point of view is a manifold, the points of which are, for example, parametrized probability distributions, but they could be parametrized amplitude or probability amplitudes in the case, for example, of quantum mechanics, of pure quantum states. We have a metric tensor on this manifold, which I call G, and a skewness tensor T. In the classical framework, the metric tensor is the Fisher-Rao metric tensor, which has interesting symmetry properties. It is the unique metric tensor which is invariant with respect to the class of stochastic transformations, while the skewness tensor is introduced because in connection, well, together with the Levi-Civita connection of the Fisher metric, it gives the possibility to define a one-parameter family of affine connection, which are dually related, which means that nabla and nabla star fulfill this equation. And what is interesting, a statistical model may be completely extracted from a divergence function. So you give me a divergence function on the manifold, and I extract from it a statistical model, so a metric tensor and a skewness tensor. But what are these divergence function? They are a sort of measure of difference between points of the manifold. They need not to be symmetric, as we have seen in one of the previous seminaries. In fact, the radius of the spheres, the divergent spheres, depended on the center. This is an instance of the non-symmetricity of divergence functions. And it is always possible to find an infinite number of divergence functions from which I can extract the same statistical model. But the curious point is that these functions are two-point functions. So they are defined not on the manifold M, but on two copies of the manifold M, just like Hamilton's principal function, which depended on the initial and final position. So it is defined on two copies of the configuration manifold. So our idea was to, okay, we take a statistical model and we define a mechanical system, the Hamilton principal function of which is a divergence function for the statistical model we started with. This is always possible. Essentially, you have to define the Lagrangian in this way. And you see, we are using only, well, numerical parameter alpha and the geometrical structures of the statistical manifold. So the metric and the skewness tensor. Once you have this Lagrangian and you compute the Hamilton principal function, you get a two-point function, which is a divergence function for your model. So you recover the metric using this algorithm and the tensor using this other. And these are precisely the algorithms used in classical information geometry. So given a statistical model, I can give you a mechanical system, the Hamilton principal function of which generates the statistical model. So the Hamilton principal function is a divergence function for this model. But I don't want to start with a statistical model. I want something more. I want to choose a specific divergence. So for example, I don't know, the Kullback-Leibler divergence. And I want to find a mechanical system of which this divergence is the Hamilton principal function. Is this possible? So this is an inverse problem for divergence function. And as it often happens with inverse problems, the general answer is very, very difficult to find. So at the moment, we don't have a global solution of the problem, but we have an interesting specific case, which is the case of self-dual statistical manifold. These are statistical models for which the skewness tensor is identically 0. So there is only the metric tensor containing every geometrical information on the model. In this case, you do have a canonical divergence function, which is essentially the capital D function, which is related to the Riemannian distance function associated with the metric. So this is canonical, and we find, it's very easy, that the Lagrangian I gave you before, so this one, for the case of self-dual statistical manifold, so when t is equal to 0, reduces to the metric Lagrangian, and it solves the inverse problem. So the Hamilton principal function associated with the metric Lagrangian is precisely the canonical divergence function of the self-dual statistical model. Of course, there could be topological problems if the Hopf-Rinow theorem does not apply in that case. This is related with the completeness of the manifold, which was a question that was asked sometimes before. But if you are not in these pathological situations, and when you do information geometry, you often are not in this pathological situation, then the answer is true and is complete. Now, an interesting example of self-dual statistical manifold which goes beyond the framework of information geometry is given by the pure states of quantum mechanics. Now here I will focus on finite level quantum systems, but you can do everything in infinite dimensional case, provided you use the notion of Hilbert manifold and you take care of some technical details. Essentially you have the Hilbert space of the system, you have the complex projective space, which is the space of pure states. And this is a homogeneous space for the unitary group of the system. This is very important. So we take a vector in the Hilbert space and we associate with it density matrices, so a pure quantum state, and we select one of them as a reference state for the quotient procedure. And we want to do this, why? Because we want to write the dynamical system not on the complex projective space, because this is a highly nonlinear manifold and we should use coordinates when working on it. We want to use the Lie group. Why? Because the Lie group has a global differential calculus that allows us to completely forget about coordinates and perform every calculation in an intrinsic way. So we define the Lagrangian, as you can see there, where the theta are velocity-like variables that are defined on every Lie groups and are globally defined, so they are not coordinates. The G is just a constant matrix, and what can we do? We simply consider the geodesics of these models, which are given, as you can see there, and we calculate the integral, so the action functional. In this case, since the Lagrangian is a constant of the motion, we can simply take it out of the integral and substitute to the velocity the expression, final state in terms of the initial velocity and the initial state, of course. And this essentially is the canonical divergence in the case of pure quantum states, which has a nice interpretation because Wouters in the 80s, I think, yes, showed that this is a notion of statistical distance between quantum states, which is connected with the distinguishability and with statistical fluctuations in the outcome of measurements. So it has a very direct interpretation in terms of recording procedures for a quantum states. So in conclusion, what we have seen is that there is a connection, very interesting and deep one, between divergence functions, which are natural objects in information geometry, and the solution of the Hamilton-Jacobi theory in classical mechanics. And so to every statistical model, there is an associated mechanical model, the Hamilton principal function of which is a divergence function for the starting statistical model. And we pose the question of, is it possible to essentially solve the problem, this problem, but not starting with the statistical model, but with the specific divergence function? And a partial positive answer has been given in the case of self-dual manifolds, but in other cases the situation is quite more difficult. And why should we be interested in this? Essentially because we would be able to give a dynamical characterization of specific divergences, and since in some cases very good divergences are relative entropies, we could define a canonical mechanical system which is associated to an entropy. So it becomes natural to ask what is the physical interpretation of these dynamics of entropy. And from the algorithmic point of view, let me say, you can, by introducing the dynamical formulation, you can manipulate symmetries using all the machinery of Lagrangian mechanics, which is well developed and could give some insight on symmetry properties of the statistical model considered. So with this, I essentially finish my presentation, and I thank you for your attention.
Okay, other questions? Okay.
Okay, so okay, I very much appreciate the effort in trying to link information geometry with geometric mechanics, basically.
Thank you.
This attempt, this is an important attempt to trying to bridge the two fields, right? Because given large similarities between, the use of Legendre transform, for instance, but the approach you adopt here essentially would result in the Hessian geometry, which is a very special kind of information geometry, because the metric you get is the Hessian metric, the second derivative of the of your potential function. Okay, so a more fruitful way to go about linking information geometry and geometric mechanics is actually through discrete geometric mechanics, where you actually look at the symplecomorphism between M cross M, the two copies of the M that you study here, with T star M. So look at the symplecomorphism, because in the T star M you have a canonical symplectic form, and with the divergence function there's a canonical way of generating a symplectic structure on M cross M. So by that link, we actually can advance, or basically look at the divergence function as a generating function on M cross M.
But this is exactly what happens here.
This is not what happens here, because
Yes.
no, this is not. Let me explain. Because here, what you're doing is that
when you get this one, this does not generate an Hessian metric, because this is a two-point function.
yes,
So you cannot take the two derivatives. You have to take two derivatives and then go to the diagonal. And this link, you can have it only, let me say, if the system is completely integrable. So if you have a local symplectomorphism between the tangent bundle and M times M. Otherwise, this function does not work. It's not smooth.
You are pulling back. Well, here you have not pulled back the symplectic form of the T star M to
I
TM.
do not.
You do not do that. Yes, right. The reason is that because in the standard mechanics, there is a Legendre transform that link the Lagrangian with the Hamiltonian. But in doing information theory, one want to relax that link. So we do not want to enforce the linkage of the Tm and T star M via the Legendre transform. And by the way, there is a paper that we just recently published in the Journal of Entropy that specifically addressed this issue.
I would very like to know which paper is this.
Okay. Any other question? Okay.
May I ask you one question? The metric tensor is just not on statistical manifold, not constant. So it I think it should be Kodachi type. Okay, the metric tensor should satisfy Kodachi type. Then, what kind of where in your talk that kind of property is used?
I don't know. Are you referring to a specific property of the metric tensor?
Metric tensor is a Kodachi type, okay?
Yes. In the quantum case, it is the Fubini study metric.
Then in your talk, where that kind of property is used?
in the quantum case,
Ah,
are you referring to the quantum case? Here,
Yeah.
the metric is, I know what metric is. It's the Fubini-Study metric tensor. And this has to be precisely this tensor because it's the only one which is invariant with respect to the unitary group. So it is similar to the Fisher-Rao metric tensor in this respect. And with this Lagrangian, you generate this kind of metric. So you don't have to require anything more than just this Lagrangian. I don't know if this answers your question.
Okay, thank you very much. So let's thank the speaker again.